Good afternoon. Welcome back to the second part of the Asia Pacific Research Platform and Data Mover Challenge session. I would suspect that my good colleague Yves will be very late at night now. So I'll take the opportunity to introduce our next speaker. Another good friend of ours, Dr. Ji-Hong Moon from KISTI in Korea, who will be giving us an update on our APAN Asia Pacific Research Platform Working Group. Over to you, Ji-Hong.
Hello everyone, I'm Jung-Hoon Moon, working for KIST in Korea, for especially working for Korea, which is Korea Research and Education Open Network. And also I'm in charge of APRP working group in APAN, which is Asia Pacific Research Platform Working Group since 2018. Today, I will be talking about updates on the APAN APRP Working Group and introduce building a high bandwidth distributed HPC project as a Asia Connect project, the fifth core by NSCC. The APAN, the 53rd, will be held next week, so I will talk about the summary of APAN, the 52nd, and introduce APAN, the 53rd, shortly. The order of presentation will be from introduce of Asia Connect project and followed by the APAN update because the APAN, the 53rd, is still before the start. From now, I will talking about a new project which is the building a high bandwidth distributed HPC. This slide is an overview of this project. Title is building a high bandwidth distributed HPC. It belongs to work package 4, and the participant countries are 4, which is the Korea, Australia, Malaysia, and Pakistan. Duration is from the 1st of March 2022 to 28th February 2023. And the requested budget is around 150K euro. And the lead applicant is me. And we have 4 co-applicants, who is the Andrew Howard from NCI in Australia, Asif Khan from the Perdana University in Malaysia, Noor Asilawati Abdul Hamid from the UPM in Malaysia, and Cees Asif Raja from the Sukur IBA University in Pakistan. This slide is the background of this project. The data explosion in science and technology drives the demand for high capacity networks for accessing computers and the storage and the collaborations simultaneously. It brings many restrictions on the generation, transmission, and the utilization of research data. In recent years, the ESNet and the UCSD, the quality tool in the US, have developed and utilized the science based big data superhighway to send and share scientific big data with the leading research institutes, universities, and institutions at ultra high speed. In the case of the US, it was carried out as the national project supervised by the NSF, the Connecting Science and the Technology Research Institute in the western part of the US to Science DMG and enabling high-speed transmission of big data. We call this project is PRP project, Pacific Research Platform. And it is currently expanding to the entire US National Research Platform. We call this NRP. In addition, this big data network-centered infrastructure system is expanding and developing into the global environment we call Global Research Platform, the GRP. And it is evolving to enable the connection with analysis platforms and artificial intelligence platforms for big data processing. They built a shared environment of IT resources dedicated to science and technology by linking various computing resources through a big data network. This made it become possible to share high performance computing resources. For example, The figure 1 shows the distributed computing resource integrated through PRP infrastructure and the scientific result about the analysis of CO2 using the distributed computing method. It is possible to link computing resources distributed to research institutes through the big data network infrastructure without possessing high-performance computing. It means that a specific researcher derives research results without possessing high-performance computing. The figure 2 shows the flooding research using distributed computing resources and the science data for LSTM analysis method for climate analysis. The infrastructure links distributed platforms at many career research institutes through the National Research Network. The participated institutes share the HPC resources for their researches. On the other hand, some Asian researchers are suffering from a poor computing environment and a lack of IT infrastructure. Although the network level of higher education institutions has improved through their national research network, high-performance computing resources for research do not meet the needs. In the case of Pakistan and Malaysia, there is a lack of public HPC resources at the national level. So the utilization of HPC resources through shared HPC is being studied, but it is insufficient. This project proposes a method to enable public high-performance computing resources to be delivered to underdeveloped and developing countries in Asia through T-Network. We propose the platform that transmits not only the data over the network, but also the computing resources. In this proposal, we aim to establish a science DMG-based research platform, a high bandwidth distributed HPC environment, and it will be shared in Korea, Australia, Malaysia, and Pakistan. That is, we will build high performance computing servers that provide the computing resources by CPU, GPU through a specially designed high bandwidth network over time. And it will be learned for bioinformatics-based science research in Malaysia and AI-based research in Pakistan. So this is the project basic concept, the configuration, high bandwidth distributed HPC as shown in the figure. The World Science DMG-based high bandwidth networking architecture is designed in participating countries via TAIN. We will interconnect available computing resources in a distributed manner. The resource of computing servers will be managed by container cloud technology and the blockchain authentication for user account. And the role of each participant are the South Korea and the Australia providing the infrastructure expertise and the infrastructure capabilities, and Pakistan and Malaysia providing application expertise. To implement this, it is divided into 3 activities, and each will achieve the detailed goal of activity 1, building a big data superhighway based on TAIN. Activity 2, the building a distributed HPC platform, and activity 3, the presenting pilot use cases. Activity 1 will implement science DMG technology to improve the utilization performance of the physical network based on TAIN, while activity 2 will implement the container cloud technology and the blockchain authentication technology for a user authentication system to the distributed HPC, relying on a high performance physical network. Activity 1 and 2 are applied to all participating institutions to establish big data and high performance computing transmission and sharing environment among the participating institutions. AI-based and bioinformatics-based science research applications and use cases can be implemented in the 2 Asian beneficiaries. As a part of Activity 3, these applications are meant to improve the educational and the research functions of the institutions. As I mentioned, we have three strategies. Activity 1, the building of the big data superhighway based on TAIN. There are CREONet, ARNet, MILEN, and the PERN, and the deploy Science DMG and TTM. Activity 2, the building of distributed HPC platform. It means that the research platform which built by Kubernetes and managing CPU, GPU memory as a computing resources. Activity 3, the presenting pilot use cases. There are two pilot use cases, bioscience and AI science. To building a big data superhighway based on TAIN. The TAIN network is an international research network that connects Europe and Asia, and it serves as an IT infrastructure for Asia's underdeveloped and developing countries. Through this project, the research network of 4 countries will be linked around the TAIN network, and the connection between participating countries will be established in a Science DMG type, big data, high-speed transmission environment as shown figure. In particular, Science DMG technology is applied for optimal transmission performance for a given bandwidth, and through the construction of a network monitoring system, maintain the big data superhighway performance. There are 3 steps to enable these environment. Interconnection, the participant enhance via TAIN. To build a big data superhighway system, CREONet, Korea, ARNet, Australia, MILEN, Malaysia, and the FUN, Pakistan of participating countries are linked with the Science DMG technology through TAIN. Installing DTN at each participant institute. The institution construct a Science DMG environment by building a DTN, which means a data transfer node, which is perform a transfer accelerator function. DTN is used not only as an accelerator for data transmission, but also as a container-based distributed computing resource. So it is used for various computing tasks based on the CPU, GPU, memory, depending on the needs of the application researchers. Third, measuring the Science DMG using a monitoring system. The big data superhighway system is constructed through the mutual trust zones of each institution. Therefore, in order to guarantee the performance of such a network system and the computing resources, they are monitored in real time through Persona and the Prometheus-based Grafana. To building a distributed HPC platform. So distributed HPC is implemented by linking computing resources existing in each institution on TAIN-based Science DMG, built with a high performance. Computing resources of each institution are linked through the DTN to share computing resources in a high-speed transmission environment, and it implements the authentication system using blockchain technology as shown figure. There are also 3 steps to enable this platform. The first one is building a platform to manage CPU, GPU, computing resources, including the storage. To building a container-based cloud platform that will provide not only a single container, but also the programmable environment to orchestrate with remotely distributed computing resources. This platform is to provide the high-performance computing power with the distributed computing resources. The developed system will be able to collect the CPU, GPU resources for large computing power to computing a big job. Therefore, a single large active job in use will be able to use the whole computing resources like HPC. So we are using a Kubernetes to build a platform. The Kubernetes is used to manage the CPU, GPU resources with the containers and the SEP storages. Building the second one is building blockchain-based ID federation. to manage a user account using a blockchain-based self-surveillance identity technology that allows users to control the use of the personal information. Third one is building an easy user interface. It provides an easy user interface by building a portal that runs on the platform over a high-performance network. And AI and the bioinformatics science researchers and the university's students will use this system. This is the activity 3, which is presenting pilot application use cases. We intend to establish a platform where distributed resources can be used as HPC resources and demonstrated the use of the AI and the bioinformatics science targeting Asian beneficiary in a high-performance network environment as shown figure. It will be supported a high throughput science research and contribute to human capital development to produce scientists such like students and the researchers and the IT professionals supporting science who are able to perform well in the research area of the new science. On the left, the figure are use cases developed for AI-based science through our co-applicant partner in Pakistan. On the right figure are the use cases deployed for bioinformatics-based research through our co-applicant partner in Malaysia. This table is the deliverables of this project. The science DMC built on the physical network according to each activity will generate output in the form of DTN, the network hardware. The distributed HPC function will generate output in the form of a container cloud software, which will link distributed resources based on science DMG. In addition, AI-based and bioinformatics-based science use cases for Asian beneficiary countries will demonstrate applications through training, publications, and or the formal report. KIST and NCR in charge of D.1.12, D.2.2, and the others are the applications by the Malaysia and Pakistan. This table is the official milestone and the timeline. Activities will produce meaningful result which will make up the deliverables and will indicate milestones as a table. We have 8 milestones to achieve the goal to build the distributed HPC platform. The major result of this project will be the high bandwidth distributed HPC infrastructure distributed at the 4 participating countries and application cases using this. An important outcome will be the achievement of the technology on a distributed platform that links the GPU and the CPU resources distributed in Asia countries with a high performance network infrastructure over time. The pilot use cases will also be an important outcome. The first one is the networking and the computing infrastructure over 4 NLANs based on TAIN. Second one is promoting Asia research and education by utilizing TAIN-based distributed HPC resources. The third one is several outcomes which will be delivered. It will benefit Pakistan and Malaysia, where HPC resources are relatively scarce. In case of the sustainability of the activities, the first one is using the APRP working group for managing and operating. The performance and the effectiveness of the high bandwidth distributed HPC, the achievement of this project will be continuously managed and upgraded through APRP working group. APRP working group is on the APN working group which pursues promoting research platform integrated via high performance network for better science collaboration, and it also pursues expanding to the global scale by federating with the PRP and GRP. Korea and Australia are the leading countries in the APRP working groups. The second one is expanding the use cases in Asia. The result and the outcomes of this project will serve as a proof of concept for beneficiary countries. In addition, the result and the outcome also serve for international research communities such as APBioNet. APBioNet is an international research community that is dedicated to the advancement of the bioinformatics areas. The third one is motivating the further collaborations to be attained. Countries in the low bandwidth network environment in Asia can also share sufficient high performance computing be attained. It would motivate the future national and international network improvement and the collaboration. So far, I explained about our the Asia Connect project, and from now I will talking about the AFAN, the 52nd and 52nd last year, and introduce AFAN, the 53rd, which will be held the next week. The first, let me introduce the APRP working group and APAN meeting, which means is Asia Pacific Research Platform. Since 2018, the APRP working group initiated at APAN, the 45th, 2018, Singapore. The APRP working group objectives is to promote the HPC ecosystem in the Asia Pacific and engage APAN members and ASEAN countries. And finally, towards the setting of an Asia Pacific research platform and become a part of the global research platform. Executive members are, chair is me, the co-chair is Andrew Howard, and the secretary is Asif Khan. The APAN, the 52nd, was held in Indonesia the last August, and we have 2 sessions, 10 speakers from 6 countries. 4 especially, there are 2 sessions keynote speech. One is research at the speed of thought, a golden age for the global RNA community by Yves, Poppe. The second one is using bottleneck structures to accelerate network performance by Jordi Lostrat. The country-specific updates are the Korea, Australia, Singapore, Pakistan, Malaysia, ASEAN, and the global trend. And attend is over the 30. The following table is a detailed program of session 1. This table is the detail of session 2. In particular, session 2 has several topics of technical issues. There are the RNA Together research platform development by Ki-hyun Kim from Korea. The second thing is using bottleneck structures to accelerate network performance by Jordi Rosso-Gerald. And the third one is 100 giga DTN clustering over KIST science DMG by Won-taek Hong from Korea. For more detail of each presentation, the Korea update, the deploy science DMG for national scale, we have a plan to deploy science DMG for 25 national institutes within 5 years since 2021. The first one is building big data superhighway between 25 national research institutes and the 4 University of Advanced Science and Technology for science big data. The second one is, for example, of National Research Institute of Korea is astronomy, chemistry, bio, the earth science, nuclear fusion research, medical, energy, the physics, ICT, and so on. Until last year, we deployed 9 institutes and 1 universities from the 10 gigabps to 100 gigabps bandwidth. The final goal is establishing the high reliability and the high speed transfer system without the boundaries between participants, as shown figure, for 25 institutes and 4 University of Science and Technology. This slide is the Ki-hyun Kim's presentation. The title is RNA Together Project in Korea. It is the building of the RNA Together platform, which is Korea national scale, the research platform for national institute. Deploy science DMG environment for national institute, the bio, fusion, research, and medical, astronomy, chemistry, energy, and so on. The current basic configuration of RNA together participant and their computing environment. It consists of 10 institutes and 1 university so far. The next is the introduce of a Pakistan update by Professor Asif Raja from Sukuru Ivy University, and introduce a Pakistan Education and Research Network infrastructure, which is PUN. They have a mix of 10 giga and 1 giga institute circuits and the migration to 10 giga nationally. And they have 155 megabps 10 circuit. This table is status of HPC and the supercomputing centers in Pakistan. They have 9 major facilities for several research topics. And also, the Pakistan is a co-applicant Asia Connect project, building a high bandwidth distributed HPC. They are part of the AI science and the building of platform. The next is introduce the Singapore update and the data move challenges of 2021 and 2022 by Elvin Xiang. This is data move challenge configuration of the world topologies. And this slide is a technical topic by Jordi Ross from the Livewire lab. It's kind of the AI-based high precision analysis of flow and the bottleneck performance in data networks. The first one is the flow performance optimization in high-speed network. The second one is applicable to both Ethernet and InfiniBand network to apply for the RN network, the large-scale data centers, and the 5G networks, and the cloud computing and the supercomputers. And this slide is promoting the vibrant and the relevant HPC ecosystem in ASEAN by Asif Khan, who is the secretary of APRP working group in APAN and also co-applicant of Asia Connect project. The first one is ASEAN HPC shared facilities and the common areas of research. The second thing is a shared infrastructure model. Finally, the human capacity development and the knowledge and the best practice interchange. HPC for the vital surveillance, the rapid growth of in the viral genome sequence, according to the bottom pictures. Data is available to many, but HPC resource is limited to the few. This slide is the 100 giga, the DTN clustering over KISTI science team by Wontek Hong from KISTI. Design and the development of 100 giga DTN clustering for a lost file system in KISTI, fifth supercomputing, which name is Nurion, and the transfer test between Korea and the US NERSC supercomputer. It is a topology between KISTI supercomputer and NERSC supercomputer via 100 giga path. Using the Globals Online for file transfer and the result are single 10 giga DTN, 2, 100 giga DTN is 9.28 giga BPS performance. And DTN cluster to cluster KISTI to NERSC is performance is 55.68 giga BPS on 100 giga bandwidth. The next is introduce NCI Cloud by the Andrew Howard. He is the co-chair of APRP working group in APAN and the co-applicant Asia the Connect project. Let me introduce APAN, the 53rd APRP working group session. APAN, the 53rd APRP session will be held 10th March 2022, the next week, from 9 to 12:30 GMT plus 6 online. We have 2 sessions and there are country updates, introduce applications and explain about the Asia Connect project. And there are 8 speakers or more. The 1 session keynote speech by NCI, title of a keynote speech is Introduction of NCI Cloud. So far, I tried to introduce building a high bandwidth distributed HPC project and update APRP working group in APM meetings. Thank you for your attention and listening.
Thank you, Jeong Moon. Thanks, a great presentation. I'd like to pick up from my APRP co-chair and start by inviting you all along to the Asia Pacific Advanced Network meeting, which will be held next week. Registration is free, and we've got a massive range of exciting sessions across a number of discipline areas. So we encourage you to join us at APAN 53 in Bangladesh next week. I'd like to move on to the Data Mover Challenge. We presented the awards to the Data Mover Challenge winners this morning. We'll be hearing from each of them after I give a brief introduction. What I'd like to speak about is some of the underlying rationale and technology behind the Data Mover Challenge, and then we'll hand over to each of the award winners to give us a bit of an overview of their approach and their unique technology capabilities that they brought to this challenge. So the Data Mover Challenge rationale is multifaceted. One of the issues that we've identified is that we need to find the next generation of data movement tools and capabilities able to effectively utilize contemporary 100 gig networks. But as we heard from Rodney earlier, 200, 400, 800 and multi-terabit networks are just on the horizon. So building data transfer tools and capabilities which are able to utilize these networks is non-trivial. Our goal is to try to investigate both academic and industry solutions. We want to build experience with both our high-performance computing storage and network tuning. And most importantly, we want to build trust and confidence between national research and education network engineers and establish that ongoing relationship. The older generation of network engineers are able to reach out to each other and create some of the most complicated network configurations, as you saw Professor Mambretti and Rodney discuss. These are not trivial undertakings and requires significant trust on both sides or across multiple domains. As you heard from Cees, there's a lot of work being done in terms of building the privacy and trust frameworks into the networks themselves. But as the infrastructure engineers, it's absolutely essential that we're able to work together in a confident and trustworthy way. We're also building trust between our HPC facilities. Because large data transfer reaches down into the very core of our storage, which is an essential and underlying component of our operations, we need to ensure that we have a robust security profile while still ensuring performance. So trying to balance those two goals is always a complex issue. We want to establish a long-term 100 gigabit per second testbed for the capability to allow ongoing testing from the teams which participated, new academic projects which are coming online, or to provide the capability for ad hoc high-speed transfers between each of the nodes. And we want to gather a range of tools which are containerized, able to work in a Kubernetes-based environment, the Asia-Pacific Research Platform, the Pacific Research Platform. We want to have a repository of tools which can be drawn down, which we know are performant, are secure, and can be deployed on one, two, or multiple elements of a data transfer facility. The Data Mover Challenge dataset was artificially constructed and is around between 1.8 and 2 terabytes. I constructed the dataset using actual data that was in production moving across NCI's facilities. It consists of non-human genome, satellite, mixed data type, video, text, pretty much the whole range of both large and lots of small files. The lots of small files element represents typical data collection movement between our facilities. While you may consider that a large file is more complicated, the underlying metadata operations on a file system for lots of small files often impose a barrier for data transfer to be able to be performed effectively. This is typical of a representative working data set from genome, climate analysis, and a number of other discipline areas. The Data Mover Challenge, we didn't want to make it too easy, so there are a number of constraints that we imposed on the participants. We required them to use Singularity for containerization to meet our goal of building a portfolio of data transfer tools. There was restricted access to the remote data transfer nodes from the public internet. This once again represents the reality of academic research networking, where it exists alongside, has connection points to the public internet, but is typically not directly accessible in many cases from the public internet. So participants were required to use jump access through an NSCC system to access the other DTNs. This did prove problematic for some of the teams, but we did have a capability there that they could have set up SSH tunneling. We permitted that. We didn't make it easy for people. People needed to explore the boundaries of this network themselves. One of the most difficult constraints was that we provided no root access to the data transfer nodes. This allowed the judging panel to evaluate any underlying operating system or network tuning that the participants requested, to review how that would impact both existing data transfers and to take any lessons from that and apply it to future data transfers. The challengers were also given 1 week to implement their solution and to perform their testing. The DMC21 network stretched around the world 2.5 times. We're starting to reach almost every continent on the planet. We were joined by our colleagues in KAUST this year. Australia was able to provide 2 100 gig network connections, allowing a best case scenario transfer, one reaching Europe across the Asia Pacific region, and the other one reaching Europe and our American partners across the continental US. We'd hoped that we're able to connect South America and complete our global continental network capability in future iterations of the Data Mover Challenge. I'd like to really thank all of the remote sites who participated in this challenge. There was a remarkable amount of work that went into preparing the environments, refreshing the environments between each team, cleaning everything down, bringing it back into a standard. So I'd like to thank NSCC in Singapore, our host for the Data Mover Challenge, my own Research and Education Network in Australia, ARNet, CSC in Finland, Joe and his team from Starlight in the USA, our colleagues from KAUST in Saudi Arabia, Jeong Hoon Moon and his colleagues from KISTI in Korea, our colleagues from NICT in Japan, Case and his team from Surf University of Amsterdam, And we'd also like to thank ICM in Poland, this was their first Data Mover Challenge. Previous iterations of the Data Mover Challenge network were built using globally extended virtual LANs. This proved problematic in the use case that we had in the Data Mover Challenge. We've seen presentations about AutoGoal, which is a facility to connect Lambda circuits together and dynamically build VLANs. What we've observed, though, is that there is limited experience in terms of global VLAN engineering within the current generation of network engineers. VLANs are an overlay network across our current production IP networks. This also resulted in poor visibility of the overall data flows, congestion, latency to the participants. Because we were running a virtual network over a physical network, they weren't able to see what other traffic constraints, other traffic flows there were running over the network. We also uncovered issues with international routing, where VLAN circuits would time out from the routing tables in the intermediate period between the challenges. This provided extremely difficult to debug. So for the DMC 21 iteration, we pivoted towards using standard layer 3 research and education networks, running over our global production R&E fabric. This was to engineer for 100 gig data flows, to allow us to observe and tune real traffic flows. These networks are not used in isolation. They are our production networks which are used for data transfer between our HPC facilities around the world. This also allowed the participants to have end-to-end visibility of the latency and congestion conditions of the underlying network. A factor we considered was valuable for some of the participants who were building their own network protocols running over our common fabric. And we also wanted to evaluate the real-world performance of these tools. How fast can they actually work over our contemporary high-speed, high-performance data networks linking each of our nations? I'd like to thank our DMC 21 supporting partners, without which we would not have been able to run this. Without reading an exhaustive list, I think you can see on the slide the large number of organisations which we brought together they contributed their networks, their storage resources, their technical expertise, and of course their ongoing support and encouragement. Without all of their help as a global community, we would not have been able to put the Data Mover Challenge together. So we had a number of participants in the competition. There were 7 participants in total. One participant decided to withdraw due to resource limitations, which left us, and one team had a different approach to the data transfer question that we didn't find fell within the scope of the challenge. So the remaining teams, Team Mushashino from Japan, looked at a high-performance and flexible protocol and application challenges for high-speed file transfer in 100 gig networks. Being Japanese-based, they often need to deal with potentially complex natural disasters which have impact on the network performance or network capability itself. Their aim was to build a far more robust internet protocol able to deal with these natural disaster conditions, able to deal with failing links with limited bandwidth, and gain the most performance out of the network. Architecture, one of an Australian product, with their MediaFlux platform, which is a rich data management solution, looked at methods of replicating their large data sets across an integrated software environment. Team Fast is Good from Malaysia had a product which was able to work effectively through security perimeters and firewalls. They used their product for doing large-scale video production, video editing, special effects, and being able to work around both corporate and academic and university and national firewalls for a production service is absolutely essential. Team Globus is one of the pervasive data transfer applications and technologies within our research community, and we were glad that Globus was able to adapt their service to operate within a DMC environment, which had a number of constraints compared to their normal configuration in terms of security and the requirement to isolate the Globus service and capabilities and front ends. And Ciena, iCare, UETN were the overall winner, and they produced a remarkably innovative set of a whole stack of tools using a Jupyter Notebook front end with a machine learning capability, able to optimize both path selection, able to affect dynamic circuit configuration, able to swap out underlying protocols based on measurement and heuristic analysis, and able to utilize the network in very effective ways. All of this is able to plug into existing Jupyter Notebook-based workflows and allows a researcher to see the instrumentation of the network as part of their large science data flow. So we announced the DMC 21 award winners this morning. The Team Mushashino was awarded the most innovative and best IPv6 performance. They had a good proprietary, reliable protocol, friendly to other internet protocols, with good high-speed IPv6 use. Architecture won the most complete solution and best software architecture. They had a great system architecture design and were able to rapidly integrate their product into the DMC environment. Team Fast is Good. We awarded them the best virtualization support. Their product fits naturally into this containerization model where you can instantiate one, two, or many ends of a transfer solution from a container-based model. Globus, our go-to data transfer facility for global data movement, won the best integrated software experience based on their 20 years of experience in global data movement. They had a great end-user software design and architecture, making it extremely easy for researchers to perform, schedule, and monitor data transfers between facilities around the world. And the overall winner with best long-distance performance was Ciena, iCar, UETN. As I mentioned, they had a remarkably innovative and deep stack of network optimization, tuning tools expressed in an easy-to-use graphical interface. So I'd like to announce the upcoming 22-23 cycle of the DMC. We decided that running DMC every year was just really too much work to impose on all of our partners when we had production work to do. So we decided to move the DMC to a 2-year cadence. In 2023, we will be conducting another set of Data Mover Challenge, and we will be announcing the results at SuperComputing Asia 2024. So thank you very much. If any of you would like to contact me, my email address is there. Once again, I would like to profoundly thank all of the participants, all of our partners, all of the network providers, all of the engineers, and everyone who provided their valuable time so graciously to support this Data Mover Challenge. So thank you, everyone. We'll now move on to a brief overview of each of the teams, starting with Team Mushashino from Japan. Over to you.
Hi, can you hear me?
Yes, we can hear you fine. Thank you.
Can I start?
Go for it.
Thank you very much for introduction, and I appreciate for every support from the DMC office and the team. And this is very honorable to have a talk here today. So our team is composed of 3 institutions, 2 academic institutions, and 1 private company, NSCC, Clearing Technology, and Kyoto University. Next slide, please. Next slide, please.
Next slide, please.
So, yes, so this is the outline of my talk, and then the first background methodology, and then this DMC 21 and discussion. Go ahead, please. Next slide, please. So, I'm not sure which protocol other teams were using, but in our application, we first initially developed our original transport layer protocol named HPFP, High Performance and Flexible Protocol, which is compatible with TCP. This HPFP protocol is designed for high-speed file transfer at the top of the UDP. So this is a UDP-based original protocol. And the design concept is for the long fat network with packet loss means a dirty network. So to be honest, our protocol is not very good at maybe not very special one to the very clean long fat network. But our challenge is how fast we can make using our protocol. And we have already published many papers in details of the HPFP protocol as shown here. So you can refer if you're interested in, or you can make contact with me. Next slide, please. Maybe we don't have to talk explain deep in this figure, but I just prepared for this view graph page to tell you that this is the original HPFP. This is the original protocol, means that using the original packet header shown here. Next slide, please. And there are many techniques, which is too much to explain here, but basically pace control, congestion control, flow control, retransmission control, especially this retransmission control, we designed carefully to show very good performance on the long distance network with the packet loss. Next slide, please. And the application which we used for in general sense, our application to use HPFP protocol is as shown here. HPFP engine is basically HPFP engine we designed. Next, we added congestion control algorithm in order to get the fairness or friendliness of the network. And we wrapped these functions with a TCP compatible API so that you can replace your original file transfer application using this HPFP. And one application is the HPAF, which is similar to the IPAF3 in order to measure the network condition. Next slide, please. And our application works on, of course, Linux system, but also for example, Raspberry Pi or Windows Macintosh, because for example, if you are interested in the IoT, Internet of Things, you want to use a Raspberry Pi, but then basically, if you install this Raspberry Pi in the outdoor area, you need to use some mobile network for DLT or in the near future, 5G. But the packet loss is inevitable in this wireless network. And maybe you want to use HPFP protocol in order to get the higher performance to transfer the data obtained on the Raspberry Pi. And also server application is prepared for to work on the server system. And now our idea is that since this is a private company product, client application should be open. But server application will be maybe free, but commercial support will be available. Next slide, please. And this is the Hcp Tools, which we used in this bundle with data mover challenge. And what is interesting is that we can replace TCP protocol and our HPFP protocol. And we examine the performance of the data transfer on each network condition, on each IP, on both IPv4 or IPv6 using HPFP and TCP. And this year, the network condition was very, very good. There was no packet loss at all on any connection. So finally, we didn't use HPFP protocol, only TCP protocol. We got a better performance than HPFP protocol in any network condition. Next slide, please. Okay, next slide, please. And let me skip this this one, but we have last year we developed our HPFP tool, Hcp tool for the multiplexed connection in order to achieve 100 gigabps. Beforehand, one connection provides you about 10 gigabps even under the condition of the packet loss. But in order to get the 100 giga or more, we need this multiplexed connection technology. So let me skip, but this was important to get a good result in DMC 21. Next slide, please. And then the stream type file transfer is also important in this data mover challenge because the data file is very small and there are many files with small size. So we design a stream type file transfer using HPFP protocol as shown here in order to get the high performance. Next slide, please. And let me skip this one. Maybe this is technical discussion, so let me skip the next slide, please. And finally, I mentioned that the HPFP is very suitable in not a very clean network condition, but the performance is very good even under the condition of packet loss. For example, in this figure, even if you have a 10% packet loss ratio on the long path network, you are able to get the 10 gigabps throughput using on one channel, one connection. Next slide, please. And this is the result of this DMC 21. And I'm sorry, I made a mistake to replace figure on the bottom side. And you need to switch right two panels with the left two panels. But anyway, on memory to memory, I'm sorry. This is good. This is correct. I'm sorry. On disk to disk, you got 25 giga BPS on both conditions and on both IPv4 and IPv6. And memory to memory, you got 45 or 60 giga, depending on the network. And but what is interesting in this result is that in each case, you got almost same throughput between IPv4 and IPv6. I guess that the reason, one of the reasons that we got award of IPv6 is that we successfully obtained very high performance of on the IPv6 condition with IPv4 condition. Next slide, please. And let me skip this one. Next slide, please. And we are already, this Hcp Tools is already ready for the security add-on authentication support. Next slide, please. And we got two functions on Hcp, copy and sync. This time we used copy function, of course, on DMC21, but sync function is also very useful and available to get to prepare to use on the real cloud system. Next slide, please. Okay, next slide, please. And let me skip this one. This is a picture of configuration. And let me skip this one. Let me skip. Go ahead, please. No, next slide. Yes, next slide, please. Next slide, please. And this is the final result that we got on scenario 2, showing that almost 100 gigabps were we obtained using HPFP protocol, using two links to the line. Next one, please. So now we are going to use this Hcp tools in Japanese high-speed network condition, connecting 7 very major and 10, including 7 major universities. There are all 10 universities or institutes connected by 10 gigabps, and we use Hcp tools to exchange the data between this one and between big storage and supercomputers. Next slide, please. Thank you very much.
Thank you very much for your great update on how you actually approached and solved the data mover challenge. Our next entrant is the most complete solution and best software architecture, and that goes to Architecta in Australia. So over to you, Jason.
Thank you, Andrew. Just wait for my slides to come up. Thanks very much. During the week, we produced a solution which we've referred to as Livewire. As Andrew said, we're based in Melbourne in Australia. Next slide, please. We are people that live in the world of data, and we've realized that the world is absolutely data-driven. That was evident in the late 1990s, and that research would be underpinned by data in all forms, and that we would need to build platforms that enable us to create, to manage, collect, and correlate disparate and diverse data at some pretty fantastic scales, and that has come to pass. And in the early 2000s, we set about building a platform, and that platform is, next slide. That platform is a platform called MediaFlux. It's a data management platform. It deals with big data, not only big data, but small data. Small things can be very important to us. And in this space for dealing with research data at pretty much any scale, we've broken just about everything that we've worked with. Networks, operating systems, storage. And if we go to the next slide, these are some of the scales that we have deployments at. We've got systems ingesting 2 to 3 petabytes of data per month, every month, up to moving 4 to 7 petabytes of data around per month. And some of the file systems that we deal with have got over 6 billion files per file system. They're very large numbers of, and lots of metadata in the hundreds of billions going up into the sort of trillions range. Next slide, please. The platform itself, we are not an assembler of technologies from others. We are absolutely makers. So we've written every aspect of our platform. We wrote the database engine. which is XODB. It's an XML encoded object database. We wrote all of our file protocols. Rarely would someone in this day and age write SMB from scratch. Well, we did. NFS and many other protocols which I haven't listed up there. We wrote the web server. So when we operate in that space, we can do really clever things. Next slide, please. We're invited to DMC. This is our first DMC, and hopefully there will be more. And we took this opportunity to write during that week the data interconnect between these platforms and repositories. So we wrote the software, we set it up, we tuned it over the week, and we wrote it up in the end. And I think we got some very impressive results. Next slide, please. We ended up producing this system, which is described on this poster. So if you see that around, there's more details on there of the capabilities. Next slide, please. In designing this system, we used a few principles. Unlike others, we would use only TCP/IP. We would not use UDP. I've written protocols on UDP previously. I like TCP/IP because it is easy for most people to manage the quality of service. And previous research had shown that with enhancements in Linux kernels, you can get pretty well the same sort of speed with lots of parallelism with TCP/IP that you can with other protocols. Moreover, that we would use existing ports. And the ports that we're typically thinking about are HTTP and HTTPS. That is, that we would tunnel over those ports so that people didn't need to open up other special network ports. They can just use the standard ports that are presented. We decided not to use zero copy in the kernel. While that is an optimization to bypass kernel to user space, that would limit our ability to deal with abstract data sources. We would make sure that what we produced could deal with billions of small files and not just single large files. In fact, I was a little disappointed that there weren't more files in the challenge. They were a very small set in my view. Next slide, please. Other principles that we would use, that we would virtualize the storage at each end of the transfer and provide a platform to scale out to reach potentially terabytes per second or more of data transfer. Virtualization of storage is important. If you have to move half a petabyte or a petabyte of data from one location to another, you may not have a single storage system that can receive that. We can distribute that over many storage endpoints and virtualize that to make it look like a single global namespace. We would consider the orchestration of the getting the data ready for transfer as one of the necessary components of an end-to-end data transfer system. For example, if your half a petabyte of data is on tape, then you need to actually recall the data from tape, and as it comes off tape, be transferring it over the network. Real-world systems actually use devices like tape, or even cloud as well. So if you need to recall from cloud, we'll manage that, and then we'll manage the transfer from one end to the other. Next slide, please. Okay, so I said we produced parallel TCP/IP tunneled over HTTPS or HTTP, and we could get we could use standard quality of service controls. The system has end-to-end encryption using AES 256 encryption. Therefore, you don't need to have a separate VPN, and reduces the load on VPNs. The transfer can operate from point to point, or one-to-one, or one-to-many. So I've just shown a case here where there's 1 to 2, but it could in fact be 1 to 100 in parallel. So if you need to send data out, essentially multicasting it, we can do that over these networks. The network connections can increase in the number or reduce according to the load that the receiving end can sustain. So adaptive to the actual usage at any point in time. Next slide, please. The to get this to work at speed, it's all about parallelization. So we wrote two parts to this chain. One is a parallelizer for the data in the first place. We have parallel scanners, so we're used to scanning file systems with billions and billions of files on them, and needing to do that at speed. And we also need to read from the source file system. Well, it might not be a file system. It could be any device, storage device in parallel. So that's one part of the pipeline. And then it splits out into a parallel packet transmitter that is self-leveling in terms of network routes. If one route is slow, the others will take over to the endpoint. Next slide, please. We deal with different kinds of storage. So the DMC challenge actually had disk to disk, but the source could be tape, or it could be object storage, or it could be cloud. And at the other end, it could be any one of those combinations. And as I said, we may virtualize multiple types of storage into a single global namespace. So the platform itself deals with that. The responsibility of the network interconnect was to make that work over the network and hide away the underlying storage topologies. Next slide, please. You can set this up to scale out. So the DMC was a fairly modest environment for us. We could drive the network to the limits with single endpoints. But if you had multiple, if you had a terabit per second or 100 terabits or more per second, you can add edge nodes in the media flux configuration, and each one of those conducts data I/O in parallel. And those systems can read from source filers, such as parallel file systems and the like. They can read from those in parallel. So basically, it's a huge vacuum cleaner from A to B. Generally, you'll be limited by the slower of the storage or the network. Next slide, please. We created these as a global federation. As Andrew said, it was a little difficult getting onto the network. So we set up one controller that had a view of every other node in the network. And from that one controller, we could orchestrate or request the transfer of data to and from every other node in the network. So you can create a federation of your own nodes. So you might have a node sitting on a collaborator's environment, or they may be external systems. Each of these are controlled with authentication and authorization mechanisms. The authentication can be anything you like, from X500 directories to SAML and OIDC, etc. As well, we've got multi-factor built into this. So if you can use second devices to verify that the people are who they say they are. Next slide, please. The platform is a service-oriented architecture. Everything in there is a service. It's very hard to see on the screen here, but here's an example where we made a request to transfer data in memory from one system to two other systems in parallel. And the destination endpoints are named. That was running, but we saw that peak at around 10.5 gigabytes per second out of the box to these two locations in parallel. Everything that happens is recorded. These can be recorded for post analysis. Next slide, please. This can be orchestrated. It's not just about moving data, a file from A to B. You might want to do something like this. You might say, I'd like to go and get all of the satellite imagery that exists, that fall within some geospatial extent over the northeast of Australia, and that have been tagged as having certain attributes, so ready for publication or research approved or etc., or part of a particular project. And I'd simply like to take that predicate, use that predicate to transfer that set to another location. The system will manage the orchestration of the storage, and it will transmit in parallel over those networks, scaling out the number of parallel connections to the available bandwidth. All of these services are available in a command line terminal, can be called from any other application, and you can chain these together. So if you transfer from, say, from Melbourne to New York, And on arrival, you can kick off another workflow, and that workflow may be a computational workflow that may produce data. And at the end of that, that triggers the return of certain sets of data back to source. We've also got monitoring for each of these nodes. We can do time series. That time series can be recorded indefinitely. So you could go back 5 years and see what the network transfer rates were at that point. You may well have actually collected or modeled the network and stored that in the system itself. Next slide, please. And I think this is the final one. I just wanted to make the following point. Although actually I did hear Andrew say earlier that some of these networks would be available earlier. We never get, I work in a commercial company. We never get, but we do have 1 foot in the research space and 1 foot commercially. So what we produce pays for us to do research, but we never get access to networks like this. This is fantastic. So I've got to say thank you very much to the DMC for that opportunity to have access to an environment where we could really push the boundaries. As I said, this was our first DMC, and we really vastly improved our network throughput rate from hour 1 to the final hours over that week, and really brought this together. I'm really looking forward to the next opportunity to do that. I'd also like to thank the staff at Architecta who cleared the pathway to allow mainly me to work on this essentially as a sabbatical to write that software in the suite. So thank you very much.
Thank you, Jason. And I should mention that NCI has been a MediaFlux customer for a number of years, and it forms the foundation for our human genomics work. So it's really exciting to see the additional capabilities that Jason and his team, or particularly Jason, have written into the software to support both our current and future needs for genomic data transfers. Thank you, Jason. Great work. Our next presentation is won the Best Virtualization Award, and its team Fast is Good with a robust HPC transfer system. Over to you, TechSun, to give us an update on how you found the Data Mover Challenge.
Hi, my name is Yves. I'm from Team Fast is Good. I'm happy to present our solution, RaySync. RaySync is a high-speed data transmission solution for enterprise. Our aim is to accelerate transmission around the world with a thunder-like speed. I'm going to walk you through 5 agenda today. First, team introduction. Team Fast is Good consists of 2 companies, RaySync from Shenzhen, China, and Robust HPC from Malaysia. Both of us are focusing on delivering high-performance solutions that improve productivity and work efficiency, while Robust HPC is also focused on solutions in high-performance computing for AI and research. Here are the 6 key persons participating in the DMC 2021. Technical overview. In this challenge, we basically comply with all the DMC technical requirements except for number 8, which is the data transfer using IPv6. This is not currently support in RaySync, but we are planning to implement the support in near future. Let's take a look at the system architecture overview of RaySync. Basically, the deployment at the source site and the target site is kind of identical. We'll have one controller at each site, and then we'll have multiple workers in order to support parallel transfer. The more workers that we have, the faster the connection will be. And RaySync is basically what's similar to rsync. It supports all the functions in rsync. In addition to that, it also supports TCP and UDP protocol. One of the key features that we have is that we support wide range of storage, including local storage, NFS, SMB, and public cloud storage like AWS S3, Azure Blob, and Google Cloud Services. We can scale out the cluster by deploying more workers, as mentioned just now, and it allows to horizontally scale the performance. Here's the deployment architecture diagram for DMC 2021. We have deployed 4 Dockers. The 3 Dockers are at the source site, and 1 Docker is at the destination site. all the files that are ready for transfer will first be recorded in Redis, and then the transfer controller will get the list of transfer from Redis and initiate transfer. As mentioned before, the more racing transfer clients is being deployed, the faster the speed can be. In this challenge, we did not use the compression. And here's the overview of how to install racing in Linux. It's pretty simple and straightforward. It only takes you 9 steps to finish the installation. And here's the overview. As for the Windows deployment, it's even more simple. It only takes 3 steps. First, to unzip the package, and then run the setup.batch, and then you can immediately log in the admin portal through browser. It's very simple, isn't it? And for the DMC installation, here's a quick overview. On the client side, basically, we have done the 3 setup highlighted in blue, and the rest in the gray is actually the command that we use to query the status of the client-side agent. As for the server side, it's the same. The blue is used for initiating the server, and the gray command is used to query the status of the server. Number 3, the test and result. Here's an overview of the data transfer scope of work. Basically, we are required to do 6 different transfers from different point to different point. Here's the overview of the result. For memory-to-memory transfer, we have managed to achieve a 62.88 gigabit per second. And for disk to disk, we have managed to achieve 23.15 gigabit per second. When comparing the result to a traditional SCP in Linux, which only yield 200 megabit per second, Racing saw a huge improvement over the transfer performance. So how can Racing deliver such an impressive result? Let's look at our technology innovation. First, like I mentioned before, we support a variety of storage protocol. This makes it a very user-friendly solution for many customers. Secondly, how we handle massive file transfer. We have support for multiple thread reads and writes, and we will use all the available CPU cores in order to boost up the transfer speed. In the event that the CPU core and this speed has to be controlled, there are settings that user can actually fine-tune it. We also use connection multiplexing for improving the transfer, especially for the TCP data connection. Unlike a traditional FTP, where one TCP data connection is required per file, this will make it very slow in a high latency network, which is not the case when a user is using Racing. For network protocol, we allow the switching between TCP and UDP based on the best scenario. For example, on a network where UDP is not suitable, TCP can take over the transfer. And then we support multi-link aggregation to serve one transmission task. In short, Racing can support TCP, UDP multi-link aggregation on a single or multiple server. We also support different connection on different network ports. For example, in one of the tests, we are using 2 network ports to achieve the parallel transfer of data between the memory to memory and achieve the very fast transfer rate of 62.88 gigabit per second. In terms of reliability and high availability, Racing support a self-healing error auto-recovery process, and also can be configured in high availability mode where the controller can be active and standby by using the Linux Hcp Tools. Transfer client and server are running in load sharing. There is no single point of failure in system if it is being configured properly. On top of that, Racing is excel in delivering a user-friendly interface for customer. That's why it is widely used as an enterprise file sync and share solution. Below are some of the screenshots that show you our interface. For example, if you take a look at this one, it is so easy to share a link to a third party. My presentation will be end here, and the next I will hand over to Angela for the rest of the features of Racing. Over to you, Angela.
Thank you very much, Tetson. This is Angela. Now I will give a brief introduction of Resync standard software. Resync is a web-based software. You only need to deploy Resync on your server. The users can access the Resync users portal to transfer files with Resync client at a very fast speed. Here we go to see what features does Resync has. This is Resync users portal. Users can upload or download files or folders from server and share files with other partners by a link. If you want to make it automatically, you can even set up a sync task. Configure the path and the sync schedule, just keep Resync client running. The files will transfer automatically according to the sync schedule. Resync point-to-point transfer can help you save server transfer volume and storage. The two Resync clients can transfer files directly. Also, if you want to online preview Office files, pictures, videos, or CD files, you can do it on the Resync users portal. Now let's move to the admin portal. This is for administrator to monitor the storage, users, permissions, page customization, and transfer monitoring. You will need to configure your storage first. Resync supports local storage and cloud storage, such as AWS S3, Google Cloud, Wasabi, and a Backbase. Just configure as much storage as you need. When you create users account, you can set different directories and permissions for different users. The transfer tasks are easy for the administrator to monitor all the transfer logs of all the users. As I know most of you are very interested in the page customization, here you can replace your company logo, name, button color, background. You can do as much as you can. For more features of Resync software and a free trial, just contact us from the QR code. Thank you very much for watching.
Thank you very much for your excellent entry into the competition. The next award winner was the Best Integrated Software Environment. Our tried and true Globus toolkit, which is used pervasively throughout our community. I'd like to hand over to Raj Kumar.
Thanks, Andrew. So my name is Raj Kumar Kettimuthu. I'm a computer scientist at Argonne National Lab in the US. I'm going to provide a brief overview of our data movement solution, Globus, which provides a easy-to-use interface for moving, sharing, and discovering data in a secure and high-performance fashion. Next slide, please. So today I'm going to focus on the data movement aspect in Globus. Our solution is based on a hybrid software as a service model in which the data connect server software runs at the data source and the data destination, while the software that orchestrates the data movement between the Globus Connect servers is provided as a service, and that service runs on the cloud. So essentially, the users can submit the transfer request to the service, which will initiate and monitor the transfer for the users using the well-defined grid of TP protocol for authentication, authorization, and file transfer. It has a checkpointing and restart mechanism, and a data integrity verification is also built into it. Next slide, please. So the Globus Connect server consists of an OAuth-based authentication server and a grid of TP server. Globus allows a user to authenticate with the Globus Connect server running at a specific institution using the user's credential for that institution. And we achieve this through integration with In Common Federation. So to move data between institution A and institution B, essentially the user needs to have access to both those institutions, and they already have credentials to authenticate with the resources at both institution A and B, and they'll just use whatever credentials they would use to authenticate to institutions A and B through our integration with this in common federation. Next slide, please. So, well, maybe go one more. Yeah, go a few more. I think there's animation which probably forgot to remove that. Go one more, please. One more. Maybe another, maybe, okay. Yeah, I think that should be fine. Okay, so so to achieve higher throughput, Globus supports concurrent transfer of multiple files and also concurrent transfer of chunks of a single file using parallel TCP connections, which the other solutions presented here today also supported those kind of capabilities. But typically all data movement solutions use this concurrency and parallelism to achieve high performance, which Globus also does. Next slide, please. So since Globus uses the grid-of-TP protocol, which is essentially based on the file transfer protocol, the standard FTP protocol, and that actually has more optimizations on top of it. So to control or to minimize the control overhead, Globus allows multiple requests to be queued at the server. In a traditional FTP protocol, you basically send a request, and once that request is processed, you send an acknowledgement back, and then you send the next request, which essentially introduces more overhead latency between the requests, which we can avoid by sending requests and queuing them ahead of time in the server. So once the server is done with one file, it can immediately move on to the next file. Next slide, please. And Globus provides a strong integrity verification through comparing the checksums of the files at the source with the checksums of the files that were written at the destination after the transfer. So what it does is it computes the checksum of the files at the destination by reading them back again after it is written to the storage system, just to ensure that it was not corrupted even when it was written to the storage system. So, but to minimize the overhead, we basically overlap the checksum computation of the previously transferred file with the transfer of the current file. Next slide, please. So, I mean, when Globus was designed originally with the grid-of-TP protocol, it had this notion of striping, which is essentially a server-side striping. So if there is a large file and you want to, I mean, it's a huge file, right? I mean, then you want to chunk them up, and you want multiple physical servers to transfer them in parallel. Say, for example, if you have a terabit network, and if you have, let's say you want to transfer a petabyte file, and you have a terabit network, and you have 10 100 gigabit nodes connected to the terabit network, right? So essentially, to utilize all the available bandwidth, you want to split that file and make the like multiple machines, the 10 nodes, the 10 DTNs transfer that file in parallel. And that control was totally within the server in the original implementation, but now we actually added the ability for the client, which is the service that is running on the cloud, to control this striping, which we call client-side striping. And the striping capability essentially improves the speed of single or few large file transfer. The transfer request that has only a single large file or few large files, they'll benefit the most with this capability. Next slide, please. Then we also developed this connector abstraction, which allows us to interact with multiple different storage systems. For example, including a number of cloud storage systems and tape-based storage systems, in addition to the traditional POSIX-based file system, which includes the parallel file systems as well. But with this, you can essentially utilize any custom interfaces that the high-speed parallel file systems provide. Yeah, I mean, these are some of the new capabilities that we recently developed. I mean, this is based on the data storage interface that was originally in the grid FTP design, but we had to make some enhancements to integrate with the newer storage systems, the object-based storage systems. And that's all I have in terms of the solution capabilities. And I'd like to give a shout out to the team, the organizers of the Data Mover Challenge. I understand that it's a huge effort, and they put in an extraordinary effort to support all these teams doing all the work, and this wonderful test bed to have. And I'm excited that Andrew and company are considering making this a permanent test bed, so we can actually test any new solutions, any new features on a routine basis. I mean, the round trip time and the locations, the available bandwidth, it's all amazing. I mean, it'd be a great test bed to have all year around. And one other thing that we were able to test quite a bit with this challenge is the IPv6 capability, which is still an experimental feature in the production global service, but we were able to test that out, and it worked really fine. We were so excited about that. So we'll hopefully make that available for all the production transfers in the near future. And we ran into a lot of problems, but the team helped us quite a bit in overcoming those problems. So thanks a lot.
Thanks, Rajkumar. Our final and overall winner, Best Long Distance Performance and Overall winner, Ciena Corporation, International Center for Advanced Internet Research, ICAIR, and Utah Education and Healthcare Network, UETN. So over to you, Daniel, the overall winner of DMC 21.
Hi there. Good day to everyone all across the globe. This is Gaurav Deepshani from Ciena Corporation, and I am extremely happy to present to you the winning solution for Data Mover Challenge 2021. The title of our challenge is Optimize DTN as a Service, and this was developed in collaboration with iCare and UETN from United States. This presentation will be co-hosted by Seong Yu and Daniel Eveling from iCare and UETN respectively. Next slide, please. While working with RNE networks and applications that use RNE networks, it was very evident that massive scientific data flows are time-sensitive, yet extremely fragile to transient system characteristics and the underlying capabilities of the system. As such, achieving a very high guaranteed and consistent disk-to-disk throughput is a challenge, which is dependent on many moving parts, such as the DTN hardware, OS parameters, software and orchestration stack, the transfer protocol, file management, algorithm, etc., and all of which need to be customized according to the application and the network and the system. And so there is no single optimization strategy that can be applied globally. While thinking about this challenge and while thinking about designing an ideal big data transfer tool, we we divided that challenge into 5 different paths. Our vision was an ideal big data transfer tool to have the ability to be able to connect to the DTNs and the edge systems, and to be able to apply optimizations and configuration changes based on the installed hardware. The tool should also be in a position to select and implement a specific data transfer protocol that would reduce the overall I/O overhead and direct the data transfers to the end process. Like Mr. Howard was mentioning, the DMC dataset consisted of large and small files both, and managing small files is a massive overhead in terms of metadata. So the data management entity that would help optimize file sizes to achieve the maximum throughput was naturally a requirement of this tool. Security and identity management were extremely critical pieces of our ideal tool, because we would want our tool to be compatible with existing frameworks in the industry. And as everyone knows, the underlying conditions are transient with fluctuating load levels and changing network conditions. So static optimizations were found to be not suitable in generic cases. Real-time predictive analytics was a block that we thought would be extremely pertinent in this solution. That will help us monitor what changes are happening around the system and the network, and be able to tune our strategy towards that. Next slide, please. With these 5 points as the motivation, we proposed a solution called as the Optimized DTN as a Service, and which was developed using iCare's DTN as a Service software controller. The iCare's DTN as a Service controller provided an excellent framework for us to connect to DTNs, and provided APIs for us to extract data out of the end systems and be able to exchange control messaging. The proposed solution was designed to be able to support a variety of different transport protocols, such as APRP, Hcp, NVMe fabrics. In this specific data move challenge, we chose NVMe over fabrics as a transport protocol to mitigate some of the control, moving parts that I mentioned in the previous slide. CLOGON was chosen as the federated identity management for uniform access management across RME networks. And finally, we implemented a small proof of concept based machine learning module that will help us estimate the performance of the transfer based on past and existing network conditions. Next slide, please. So this brings us to the overall high-level architecture of the Odas solution. The 5 points that I mentioned previously have been mapped here. A Jupyter notebook at the front interfaces with the user. The DTN as a service controller interacts with the system underneath to make optimizations or configuration changes. A variety of transfer protocol stacks are available to be selected and implemented, and the data transfer node hardware is identified and optimized. Data is extracted from the end systems and if possible from the network in between, and the data is ETL transformed and stored in suitable databases. A transfer analyzer, which would also function as a machine learning regressor, would estimate how the transfer or how a future transfer is going to look like given the existing conditions, and then recommend that feedback back to the controller. We'll go over the specifics of the solution that we proposed, and I'll hand it over to Sion to take it from here. And next slide, please.
Thank you, Grapdeep. So we developed this DTN as a service framework to be able to provide DTN functions to the users. So we try to create a big data movement workflow to match with the existing big science data flow. Our philosophy behind it is to be able to provide different DTN functions, such as moving big data and analyzing the real-time performance of the data transfer to the users, so they can manage and orchestrate and monitor the existing big science data flows. Our goal for implementing this DTN as a service framework is to improve data transmission performance over high-performance networks, especially for the cluster environments such as Kubernetes. It is critical to be able to access the low-level hardware from the cloud environment to be able to make use of the full potentials of the high-performance hardware and storage solutions that is being powered by the DTN architecture. So we made sure that the API that we provide can optimize and detect and set up and optimize existing hardware and software architecture in each DTNs in this DMC, and properly set up and tuned for a specific transfer flows. One of the other advantages of using DTN as a service in this DMC is to be able to experiment with a container native service in DTNs, such as direct access to the NUMA architecture from the containers, and direct access to the NIC functions, storage management functions, especially for NVMe over fabrics and NVMe over TCP, and transfer protocol optimization and monitoring of the system networks. And we also have enhanced additional capabilities of controlling NVMe over fabrics from the containers. Next slide, please. So the NVMe over fabrics provide a next generation DTN functions for a data movement. In the traditional big data transfer has to move a data from a remote location to the local storage by doing a storage read on the remote location and storage write to the local location through the high-speed networks. And then the local user or user application has to read from the local storage devices again for a data access. But using the NVMe over fabrics, you can now directly access the remote NVMe storage devices, just like you're reading it from the local devices. So this is potentially very useful for a traditional application that is designed to work with local storage and without having a data copy overhead that is coming from the traditional data transfer. Next slide, please. So I will hand over to the detail of CI logon integration to the Daniel.
Thanks, Sion. Yeah, so one important feature of our solution is CI logon. So CI logon enables user access from different organizations to this same system, to our orchestrator and our DTN as a service. Because CI logon includes thousands of IDPs across research and education institutions, as well as commercial entities like Google or GitHub, users outside of the hosting organization for any supported data node are automatically supported. So this makes the DTN as a service controller easier to use, and it allows access to multiple users without sharing accounts or logins. Next slide, please. So you can see in this case, for CI logon. This supports a few education organizations on the same system. Next slide. So each user has their own account on Jupyter Hub, which is our main interface for interacting with our solution. Since they've got their own account, notebooks are not shared among other administrators on this controller. So what this means is that user data can get passed to the DTN as a service orchestrator and controller, as well as each data transfer node running our agent. In the future, with some improvement that we can do, this could be used to allow many users from different organizations to use the same controller, but only be restricted to DTNs that they have permission for agreements that they have worked for different organizations or institutions. And what this CI logon authentication and federated identity piece is allowing access to is our Jupyter client. Next slide, please. And what this gives us is an object-oriented programmable interface for our solution. So this is a Python client for our DTN as a service. And what this lets us do is set up DTN objects in code. And with that, you can orchestrate transfers, run transfer bandwidth tests, explore file systems and all of that, all in one interface that can be programmable. So, tests or transfers can be automated, for example, or it can be integrated into existing Jupyter workflows. Next slide, please. And here I'm going to pass off the our transfer analytics to Gauravdeep.
Thanks, Daniel. Yes, and this brings us to the last part of the solution, the real-time analytics and monitoring part. Our approach for using analytics was to extract data from all possible points of ingress and egress in the network before the data transfer begins and while the transfer is happening. The process would construct a data set out of this extracted data and using lightweight machine learning algorithms predict the kind of performance a specific future transfer would experience. The user would then use that feedback and a ballpark estimate from that approach to fine-tune their strategy of how they want to implement that transfer. There are a variety of different possibilities of what kind of parameters you want to optimize for this data mover challenge, and the kind of transfer solution that we chose. The transfer strategy specifically translated to choosing the number of worker processes for parallel transfers, choosing the right block sizes for reading and writing data, and choosing the right file sizes for compression and decompression. And based on this feedback and a very initial version of our analytics approach, we were able to achieve relatively high levels of accuracy when compared with our test data set. Next slide, please. The workflow would, in short, look something like this. A user process would interact with the Jupyter Hub and CI logon front end, which would connect with the DTN as a service controller at the back end to instruct on the DTN tuning and setup instructions and the transfer protocol instructions. Which would then get translated into specific configuration changes on the DTN, or if you have visibility into the network changes in the network settings. All of this would continuously be monitored and tracked by our analytics engine, and the AI-assisted flow optimizer would then recommend tweaks to sudden changes in network environments or system load conditions, and optimize the data transfer strategy, the ongoing data transfer strategy, or suggest different parameters for a future transfer strategy. Next slide, please. We had a very interesting experience with the DMC network. It was a challenging network, to say the least, which brought out the fun in the competition. And we're very thankful to the organizing committee and all the hosting institutions for providing a dedicated network for us to experiment with. Some of the insights that we gathered from our tool set was these data transfers are extremely sensitive to latency between nodes, CPU utilization, I/O wait times, the file sizes that has been used, and like Mr. Howard was mentioning, especially in the case of lots of small file sizes, the metadata turns out to be a massive overhead. The number of processes that have been used for the transfer, and the block size that has been used between the files. There isn't we also observed that there isn't a direct deterministic way of finding which of these and what of these parameters should be used. So depending on system conditions, these parameters keep on fluctuating from a wide range of numbers. And this is where we think the analytics approach can help us give us a ballpark of where to start with a transfer strategy. Next slide, please. Given that, there's a lot of extrapolation that can be done to this approach. This was our first participation at the DMC and a very first attempt at capturing system and network data both during the transfer and before transfer, and using that information to make an informed decision for future transfers. And there's a wide variety of decisions and the directions that can be taken to make the data transfer process as consistent as possible. We would envision our processes to become data acquisition processes to become smoother, and our data set to become richer by extracting more network data, for instance, buffer or port-based statistics from the network that this flow traverses through. And also enrich the data set through getting more compute statistics with privileged access, which was not possible during the DMC challenge week. In this proof of concept, we developed a very lightweight machine learning regression algorithm, but we think there are many different approaches to that we could incorporate, which would enhance the transfer strategy along the lines of reinforcement learning, online learning that can help track changes better. We would also like to compare different transfer protocols on similar DTN pairs, for instance, NetSCP versus NVMe or Fabric, to be able to better characterize the effect of control message exchanges in these protocols. And last but not least, we'd be open to collaboration and testing out this mechanism in wider networks that have a containerized environment. And that brings us to the end of our solution. Thank you everyone for listening to this. And once again, thank you to the committee for hosting this challenge and recognizing our solution as the winners. Thank you.
Thank you, Gauravdeep. As you've heard, we've had a diverse range of completely different approaches to the challenge. As a judging committee, it challenged us to try to determine how such disparate ways of dealing with this problem, how we could actually select a winner. We thank everyone who participated. Each of you brought unique capabilities, a unique viewpoint to this challenge. You've also challenged us in terms of making the challenge a little more complex next time. And we would invite you all to join us for the next iteration of DMC. And we really look forward to seeing both your next iteration of solution and other solutions that come along. So this brings us to an end of today's session. Thank you, everyone. Thank you for all of our partners. Thank you for the judging panel. Thank you for our national research and education networks. And thank you all for listening today. Have a good evening, and we'll join you tomorrow at the final day of SuperComputing Asia 2022.